Doppler effect is a particular different thing. We'll come into that later. So the main difference where it is coming from, it is Heisenberg uncertainty principle. So it is true that this energy state may vary, but that's not varying because of the electronic state, but for a quantum mechanical phenomena. So before going into the details of that, can anybody explain me what is Heisenberg uncertainty principle? Anyone?
So that the product of change in energy and the change in velocity, like change in momentum and distance, so should be greater than or equal to h by 2 pi. Like it
Oh,
has to be
very,
greater than that in this
very
systems.
nice. So that is how we generally learn Heisenberg uncertainty principle, that the uncertainty in the measurement of the momentum and the uncertainty and measurement of the position at the same time will be greater than or equal to h cross. H cross means h by 2 pi, as Nikhil has just said. However, Heisenberg although proved his equation like this, but that is not the only two parameters that obeys this Heisenberg uncertainty principle. There are different combination of parameters also follow the same trend. And I'm not going into the details of quantum mechanics, but all those parameters are such a way that it actually gives you the 4-dimension information about the system itself. For an example, momentum. What is momentum? Mass into velocity. So mass is a dimensional equation. So you can leave it. What is velocity? Distance traveled by time. So you are getting some distance, that means XYZ parameter, that means 3-dimensional parameter, versus time. So that means the time parameter is coming. Position itself is a XYZ parameter, so you are getting the 3 dimensions. So over there, by these two parameters, you are going to get the information about all the 4 dimensions. So if there are two kind of commutator parameters, which actually gives this kind of equation and gives you the idea about all the 4-dimensional system, about that 5-dimensional information about the system you're talking about, they can obey this particular law. So momentum and position is one particular expression of Heisenberg uncertainty principle. When Heisenberg did that, he did this with this particular equation. That's why it is more popular, but that is not the only one. The other one is also possible, is tau into gamma. So what is tau? Tau is lifetime of excited state. It is the, again, I should say, error or uncertainty of measuring lifetime of an excited state. What is lifetime of an excited state? When we excite something from the ground state to the excited state, it generally comes back to the ground state. But before coming down to the ground state, it takes some time. It takes some time, from femtosecond, nanosecond to millisecond, depending on what is the excited state you are talking about which particular spectroscopy you are talking about. If it is IR spectroscopy, it can be in microsecond level. If you're talking about electronic state, it is in the femtosecond level. If you're talking about a different electronic state with different spin state, it can be in the picosecond level, where you see phosphorescence. So depending on the particular state we are talking about, it has particular finite time where the system stays in the excited state. And that is called the lifetime of the excited state. And that lifetime of the excited state, and you're measuring it, the error in that, it will be very similarly following the same trend with another parameter, which is known as line broadening. So what is this line broadening means? Error in measuring of the energy. For an example, we have generally measured energy as E, and we can say E equal to h nu. Everybody agrees, E equal to h nu. So now, if I am measuring a error or uncertainty in the energy, I'm measuring a uncertainty also in the h nu. Now, h is a constant, so I cannot measure a error in a constant. It is a constant all the time. So I can measure the error in nu, the frequency. And what is a frequency? Where the energy is transferring actually. So if the delta E is 0, that means delta nu should be 0. So you should get a straight line. But because the lifetime of the system, it is connected to the delta nu. So now you can think about, if it is a very short living state, it is coming back very fast, what will happen? If the lifetime itself is very short, the error connected to the lifetime will be also very short. Then this line broadening effect will be very large. That means where actually the transition is going to happen, it will always be happen in a broad area. It doesn't depend only on temperature, doesn't depend only on the solution condition. It will happen even if you do that at 0 Kelvin because of the uncertainty principle. That is another proof that the quantum mechanics actually holds true. And that is why we generally get a line broadening effect. That is because of the uncertainty of the energy value we are measuring. And that is coming from Heisenberg uncertainty principle. Everybody agrees to that? Why we are seeing a line broadening? It is a natural phenomenon. Even if you do that at 0 Kelvin, only one molecule, nothing else, you stop moving that molecule or the atom, even then it will happen. Because that is the uncertainty principle. That is the quantum mechanical fact. Everybody okay with that?
Yes, sir.
Okay. So now, once we, yes, we go ahead.
So basically, what we are understand that if the molecule's excited state lifetime is very large, then very small, then line broadening also large.
Also large, yes. So I should have mentioned that a little bit more on that. For an example, like you can see the rotational spectroscopy lifetime is actually very high. So that's why you can remember when you take a look into the rotational spectroscopy line, you can see they're very sharp. They're actually very narrow. Why they're narrow? Because the lifetime is actually already very large. So if the lifetime is large, the error will be large. And you can see they're actually multiplication condition. So if this is large, this will be small. If this is small, that will be a narrow line.
Yeah, okay.
Now you think about you're exciting a nuclear state, already giving a huge energy gap. That means it is already very excited at a very huge energy gap. So higher the energy gap, lower will be the lifetime. And lower will be the lifetime means lower will be the error in the lifetime. So line broadening will be very broad. Okay, so that is the reason. Higher the energy you use for a particular spectroscopy, generally higher is the natural line broadening. Okay. Okay. So now coming to that system. So how I can handle this system? So the thing is that even in presence of recoil based system, what I am getting that if this is my E0 where it is happening. Okay, sorry. I am getting a system like this where almost no overlap is happening between the absorber and the absorber and source system. So almost no overlap happening, and no overlap happens means no resonance, no Mossberg spectroscopy. I cannot even measure it. So that is the problem a person faced in the 1950s when we were doing these experiments. He's trying to do this experiment. On paper, he said like, okay, I should have seen that. I excite that with the same atom iron 57, I'm a same absorber iron 57, I should see an absorbance peak. And he was unable to see that. And then he was doing the math and he found because of the recoil energy, it is not matching. Because this huge recoil energy gaps, it is creating the problem. So if you are there in the same position of that particular guy in 1950s, what you would do to make sure that the recoil is less? Anyone? How to stop this recoil?
Sir, I will put it in solid state.
Exactly. So exactly that guy also thought in the same way. So like, okay, the problem is that I am actually moving it too much. So let's stop it. Let's put that in a solid phase that it cannot move at all. So how I can put it in a solid state, it doesn't move at all? I can put it in a crystal or lattice. So it doesn't move at all. Okay. And what happens? It releases the energy, and my absorber also is remaining in a very similar lattice. So it is also there. So this is my absorber and this is my source. And due to this, putting that in the lattice, what happens? My recoil is now minimal. Okay. Now, what are the different recoil positions are possible? What are the different modes? I can lose energy in recoil energy. One is the translation motion, that the molecule is moving here and there. That is one possibility. And that is now becoming zero as I'm putting that in the lattice. What is the other possibility? The molecule can still vibrate, right? The molecule can still vibrate and lose energy. Now, it is connected to a lattice. That means well-defined position of each atom or each molecule. Now, if I want to vibrate, I cannot vibrate very specifically one bond. I have to vibrate a lot of bonds all together to make sure my lattice is also keeping intact at the same time. And that is known as lattice vibration. Everybody is with me? What is lattice vibration? It is also a recoiling. So kind of like sometimes happens that you hit the bell and you can see sometimes it moves and sometimes at the same place it is just vibrating. Similar things can happen. I'm actually hit someone is a very huge force, but I'm not letting it go. So it's just vibrating at the same place. That is the lattice vibration. Now this lattice vibration can happen also following a quantum mechanical phenomena, very similar to your vibration spectroscopy. This vibration is also follow some system. So this is already zero. So E transition is already zero because of the lattice I am pointing out. And this one can happen only at particular frequencies. And what are those frequencies? It is A H cross omega. And I is different state. Omega is the frequency of the vibration. Okay, so this vibration can happen at different frequencies, but it cannot be any frequency because it is quantized, because you have to move all the molecules together. All the molecules are already controlled by their own motions, own interactions. So you cannot have any position of the vibration, a particularly fixed quantized vibration. And what is this n value? N value can be any integer starting from 1, 0 to 1, 2, 3, and so on and so forth.
Professor,
That
are
is-
you addressing something called phonon?
Yes, I'm coming into that. So that is very nice. So that is actually known as phonons. And that is one of the reasons of getting temperature in the system. Because sometimes we excite a system, when it is coming down, it is not coming as a radiation. That is what we learned, right? It is non-radiative interaction. So what is the radiation going out? It is actually creating a vibration all around the surroundings and system. And this particular lattice vibration or vibration in a solid state, it is known as phonons. And these phonons, very similar to photons, as I just discussed, actually quantized. And these phonons are going into excited state. And when the phonons coming down, it is losing the vibration around the surroundings. And when you vibrate something at very high vibrational frequency, that is